Hello and welcome to part 4 of this week's lecture. In this part, we are going to look at orifice meter and Venturi meter. Okay. Previously, we discussed pitot tube. So, in contrast with pitot tube, uh, which slows the fluid and measure the resulting increase in pressure, orifice and Venturi meters cause the fluid to flow through a restriction in order to increase the flow velocity and measure the resulting decrease in pressure. Okay. Another contrast between pitot tube and Venturi and orifice meter is that the pitot tube measures the point velocity inside the channel, while these other two meters, orifice meter and Venturi meter, both measure the average flow velocity across the whole cross-sectional area of the pipe. Okay, and here, for example, I have shown orifice meter, and an orifice meter is actually an orifice plate that is inserted across the cross-sectional of this flow, for example, and the hole in this orifice plate is smaller than the cross-sectional area of the pipe, or the diameter of the pipe. Okay, and due to continuity equation, the flow velocity must increase in order to get the fluid through the constriction. So upstream of orifice plate, the flow cannot suddenly turn, for example, around the corner when it meets the orifice plate. Okay, instead the streamlines converge to form a cone of streamlines, as you can see here. And again, these streamlines cannot, for example, suddenly change direction as they pass through the orifice meter, and so they continue to converge for some distance, that is here, and then after this distance they again for example go back to their original streamlines. Okay, so this conversion, that is just the area that is after the orifice plate, the smallest area, is called as vena contracta, and that is actually a jet of fast moving fluid surrounded by slow moving eddies. Okay, so these are the mixing eddies that are generated because of this orifice plate. And as this jet mixes with the slow moving fluid downstream, it slows down and the streamlines diverge to fill the whole cross-sectional area of the pipe again. Okay, and so the jet velocity is at its fastest at the vena contracta, that is the narrowest point, and which occurs about halfway the pipe diameter downstream of orifice, as it is shown here that it is almost half of the diameter away from the orifice plate. And the pressure at this point will therefore be the lowest because the velocity is the maximum here. And this is why we put one arm of the manometer just below the vena contracta. Okay, and the other arm is placed, for example, one diameter away from the orifice plate on the, let's say, on the upstream of the orifice plate, and these dimensions of diameters, for example, are recommended so that you don't disturb your measurement of velocity due to these constriction effects. Okay, if we now apply again our Bernoulli equation and try to relate pressure difference with velocity, we have point 1 that is upstream of vena contracta, and then we have point 2 that is at vena contracta. Okay, so if you write your Bernoulli equation and make assumptions that you have an ideal fluid, it means there are no energy losses. H1 is equal to H2, it means there are no height effects, no elevation effect. And then you can say that you have incompressible fluid, it means the density is not changing. And if you, for example, do that, you can see that we can take out H1 and H2 because they are at same height. We have these 4 terms left in the equation. And from these 4 terms, we can, again, we said that the density is constant, so we can multiply both sides with rho g, and we have this equation here, and then we can write this equation in the form of pressure difference. Okay, that is P1 is equal to P2 is equal, P1 minus P2 is equal to rho over 2 U2 square minus U1 square. Okay, but we also know the analysis that we did for example, for pitted tube, for a manometric measurement, that P1 minus P2, P1 is the pressure at this point, minus the pressure at this point, is equal to rho F minus rho G delta H. Okay, so exactly the same formulation like we did for pitted tube. You can develop it for here as well. Okay, so we have this equation. So now these both equations, the left hand side is the same, so we can compare these two equations here, and we know from continuity equation that u1 is equal to u2 times a2 over a1. So that is the continuity equation itself, and then we can replace the value of u1 in this equation here, and then you get this equation, and here you have replaced u1 and also taken out u2 as common in this on the left hand side of the equation. Okay, and then we again try to rearrange this equation and try to write it in the form of u2. So u2, that is the velocity at vena contracta, that is the maximum velocity here in the pipe, is equal to 2 times difference of densities times g delta h over rho 1 minus 8 over a1 square. Okay, and as we know that we are more interested in the flow rate than the velocity, we can calculate what is the flow rate, and that is q is equal to a2 times u2, and so that should give us the flow rate at the lower side of this orifice plate. Okay, now the problem is that we don't know what is the cross-sectional area of the vena contracta. We don't know the value of a2. So of course we know the value of the orifice plate, that is a0. So we can define the coefficient of contraction, okay, cc, that we saw in the previous parts as well. So which is the ratio of cross-sectional area of vena contracta to the area of orifice plate. Okay, so a2 should be equal to cc times a naught. Okay, and in addition to these constriction effects, we also have, for example, the viscosity effect as well. And due to the viscosity effect, the velocity of the fluid at the lower side of the, for example, vena contracta is also going to be affected. So we also need another coefficient to account for that viscosity effect, and that is what we call CV, that is the velocity coefficient that consider the effect of viscosity and the eddy formation. So we can combine these two correction factors, and we can write that Q actual should be then equal to CV times CC times A naught, that was the area of the orifice plate, times the ideal velocity, okay, that we calculated here on this slide. So by multiplying with this correction coefficients, we convert this ideal velocity into actual velocity, and then by multiplying it with the cross-sectional area of the orifice plate, we get the actual flow rate. And we can actually simplify this equation by combining CV and CC in the form of CD. So we just have one coefficient to worry about, and that is called the discharge coefficient. And this discharge coefficient is actually the value of 0.61, typical value. But the value of this discharge coefficient is also dependent on, for example, the design of the orifice plate and the diameter of the pipe, and also the precise positioning of, for example, of the tapping of this manometer legs, and also it depends on the Reynolds number. Okay, so this value is calculated based on experiments. Okay, so if we use CD instead of CV and CC, so we have this equation in the form of densities, and we know from that delta P is equal to rho GH. So we can, instead of writing densities, we can replace this delta rho G delta H in the form of pressures, that is P1 minus P2. Okay, so this is another form of the flow rate equation from the orifice plate. Okay, so you will also see orifice plate in your lab, for example, where you will you have this setup there. So here you have the orifice plate inside these flanges, and then you have these two manometric legs that are calibrated with the, for example, with this ruler here. And then you can see that when the flow velocity is increasing, the pressure is going to change, and then you can relate the pressure with this equation here and calculate what is the flow rate or what is the velocity in the system. Okay, so that is the same thing. And you have another experiment. I think some of you have already maybe done these experiments, and some of you will do it in semester 2 or next year. So then we have a similar setup or similar flow measurement device that is called Venturi meter. And in contrast to orifice meter, which uses, for example, an orifice plate to give certain contraction through which the fluid must flow, a Venturi meter uses a gradual decrease, okay, a gradual contraction followed by a gradual expansion. Okay, so here, for example, you can see you have a Venturi meter which consists of a converging section, and then you have this short parallel sided throat, that is this, and then you have again a converging section. Sorry, a diverging section. Okay. And if you apply again the Bernoulli equation, just like we did for the case of orifice plate, we will get same velocity equation. If you like, you can try to do it yourself, but it is exactly the same. You consider a point 1 here and point 2 here, and then you do the same analysis. You comes to the same equation, but the difference is that because there is no sudden contraction, you have a smooth contraction. So we can write that the C, the contraction coefficient, is 1 for the case of Venturi meter. And as such, the value of CD is also higher. So compared to 0.61 for orifice meter, now the value of CD is 0.96. It means that your actual velocity is going to be very close to your ideal velocity, because here the fluid is not facing any resistance. It is very smooth transition from a converging section to a parallel shaped throat and then to a diverging section. Okay, so your velocity is the same formulation, but the value of CD is different now. And we can calculate the flow rate from this equation again just by multiplying it with the area A2, that is the area here. And the difference is that for the case of, for example, for the case of vena contracta, for the case of Venturi meter, we know the A2 because we know we don't need to calculate it like we did for the case of orifice meter. Here we know what is the cross-sectional area of the throat, that is the A2 here. Okay, so just by plugging the value of A1, that is at a cross-sectional area at point 1, and cross-sectional area at point 2, that is A2, we can calculate, and the pressure terms or the density terms, depending on which equation you are using, you can calculate the velocity, and then by multiplying it with the cross-sectional area at point 2, you can calculate the flow rate. Okay, so this is what you will see in the lab as well, that as you can see here, so you have a Venturi meter, you have a point here, that is where you have the parallel throat section. So you have one tube here, and then you have one tube upstream of this Venturi meter. So by measuring the difference between these 2 points and using this equation here, you can calculate what is the flow rate through your pipe. Okay, so we saw that by using these meters and using the analysis of Bernoulli equation, we can actually relate the change in pressure to the velocity of the fluid. Okay, so that is all for this lecture, and I hope now you should be able to understand how you can apply Bernoulli equation to different systems, and how you can use the principle of Bernoulli's to actually use in flow measurement. Okay, and this is a slide from where this material was taken. Please have a look at it, and if you have any questions, please use the discussion board or Padlet to post your questions. Thank you so much for your time.